Chapter 2. The measurement is the metaphor. Measurement technologies reflect and extend what is known. Some people, like Rene Descartes and Sir Isaac Newton, believed that only those things that can be measured can be considered real. In their world, if it can't be measured, it doesn't exist. Measurement technologies are how we relate the unknown to the known. The four different kinds of measurement technologies reflect different kinds of understandings of the world or worldviews, not reality. To be technologically sane would be to incorporate these different worldviews. To be technologically insane would be to identify nature as data. Natural technologies of measurement. Recognition of size. A rat will not jump further than it thinks it can make, and I will not eat anything bigger than my head. Crows are able to recognize the difference between numbers of objects up to 4, but, like us, they recognize the difference without counting. Recognition of size and number is a simple form of measuring, but more abstract than a natural genetic code that gives a flower 24 petals, or me 10 fingers. Do this experiment. Get 7 coins or pebbles or anything you can hold in your hand. Choose a number of them and show them to a friend. Most of us can recognize 4 or 5 immediately without counting. 6 or 7 usually have to be counted to know how many there are. For example, how many X's do you recognize without counting? How many here? Or here? Or here? This experiment shows that without counting, we can only keep track of a small amount of things. We may try to recognize groups of 3, but can't recognize groups over 4. Counting above 4 to 7 is not innate. Numbers must be learned just as the letters of the alphabet must be learned. Artificial technologies of measurement, contingent measures, one-to-one correspondence. The basis of artificial measurement technologies as such is counting. We can count things that we consider the same. In some specific and/or general sense, 5 pears equals 5 pears, 2 apples and 3 oranges equals exactly 5 fruits. The fiction that one pear is the same as another is easier to grasp than that an apple and an orange are similar. Counting is not an innate ability, but must be learned. In the U.S. English language, we don't have words to specify over 3 things other than numbers. We have words for a sheep, a couple sheep, a few sheep, and many sheep. Anything above 4 must be numbered to convey specifically how many. In cultures unfamiliar with writing the quantity of quantities greater than 4 can be contingently counted using a one-to-one correspondence, for example, a pebble for every sheep, our word calculate comes from the word calculus, meaning small stone, or fingers, digits. I use my fingers for counting days of the week and determining how many coffees and teas I need in a meeting. Our limited ability to innately recognize higher numbers than 4 to 7 explains why there are so many contingent measures. If one measured something large, one used a large measurement. The pace is a good measure for determining the length of a garden, while the finger is better to determine the amount of liquor in a glass. Other measures, such as the yard, the space between your nose and forefinger, are a better measure for determining the length of a piece of cloth than a pace or a bushel. Originally, a bushel was as much as you could carry. The recognition of night from day is a natural technology based on internal chemical and external stimulus. Not so obvious is the distinction of morning and evening from noon, noon being when the sun is directly overhead. For longer periods of time, longer measurements are used. For example, using the moon's waxing and waning periods for lengths of time longer than a day. Notched bone moon calendars have been used by many prehistoric cultures as a way of keeping track of the phases of the moon, and the number of moons for such things as meetings and feasts. Many people cross out the days on their calendars as they proceed through the week. This is a vestigial contingent system. A way of keeping track of even longer periods of time is recounting of one's ancestors in related stories, i.e., the Great Flood of Grandfather's Day or the buffalo hide of the Native Americans, with pictures of the most significant event of the year. Today we still use holidays and special events to place occurrences in temporal context. The contingent measurements of time are derived from use and have a one-to-one correspondence. My dog had a lump on his throat, so I took him to the veterinarian. The vet described the lump as the size of a walnut. This is a contingent measurement that I could relate to, so the next day, when I felt the lump again, I could determine that the lump was bigger than a walnut. The emergency room vet described the lump using centimeters, but this was not relevant to me in my home because I don't have a set of calipers. Contingent measures are handy, convenient. Contingent measurements are derived from use. Contingent measures are used today by both civilized and uncivilized peoples. It is the conceptualization of this contingent symbolic experience that leads to the next stage where experience becomes formalized. Formal measurements, institutionalized standards. The first formalization of counting using numbers appears with writing in ancient Babylonian and Egyptian temples as a means to keep track of inventory accumulated through tribute, taxes, and other means. This is also where the formalization of measurement occurs, and for the same reason. The invention of numbers is a formal technological invention directly related to the invention of writing. Number systems allow a great quantity of things to be counted within the same system so that comparisons between quantities can be made. The formal system the ancient Babylonians and Egyptians used was based on 60 and 12. The formal sexagesimal system has the advantage that it can be easily divided in the head into 1, 2, 3, 4, 5, 6 parts without using fractions. With any kind of notation of number, there is the possibility of keeping track of the quantity of something. Accounting is facilitated by units of measurement. Measurements are formalized when physical standards are kept by the religious or political authority. Formalized measurements, like formal communication, facilitate understanding when language becomes decontextualized in space and time by writing. The original formalized physical standard of a foot may be an actual king's foot, which becomes the formal measurement standard that all other feet must be equivalent when compared to it. In the same way, the palace's scribes determined the meanings of written symbols. With the formalization of measurements, a multitude of measurements derived from use become obsolete or redefined using an institutional, hierarchical, conceptualized standard. For example, inches become correlated with feet, and feet with cubits and yards, etc. There are still various sizes of standards so that fractions are kept to a minimum. For example, we do not say that this table is 0.00104 miles long, but 6 feet. An example of a measurement that was redefined in other ways is the acre. While contingently the acre was the amount of land that could be plowed in a day, formal definitions related the acre to area, length by width. Space, like time, weight, area, temperature, etc., are formal concepts created by the consolidation of many units into a few standard units. The coordination of quantities of people is also facilitated by the use of formal measures. By coordinating the workers through hierarchical control, the builders of the pyramids could specify the number of royal cubits, forearms, and refer to a physical standard allowing different workers with different forearms to coordinate their work using measuring sticks derived from the standard. A great invention of formal measurement is the annual celestial calendar. When we say that spring is late this year, it is not spring that is late, but our calendar conceptions which are early. The solar calendar is dependent not on the contingent environment, but on astronomical observations, and has a predictive power much different than the natural signs of the season. This power was used in ancient Egypt, where there is not much distinction between seasons, but the Nile floods predictably at the same time of year when Sirius, the dog star, rises on the horizon, coinciding with the melting snows in the interior of Africa. Being able to predict the floods and use other formalized measurements gave the priest rulers enormous power to coordinate labor space and time on their estates. The power to organize the year using a solar calendar was also exploited by the Catholic Church in Europe, The year was marked with planting and harvest festivals and saints' days. The formal celestial calendar make the seasons appear to revolve in a perfect God-given circle, but then the inexactitude of the measurement of this circle led to a crisis in the 1500s in Europe. The solar calendar that Julius Caesar had put in place in Jesus' time was not in line with the sun, stars, or seasons anymore. The Julian calendar interpreted the solar year as 365 and a quarter days like ours. But every year, the calendar drifted 11 minutes and 14 seconds. Enough of a drift so that after 1,500 years, the calendar was out of synchronization by about 14 days. The Gregorian calendar introduced an additional leap day every 400 years. The Gregorian rearrangement of the calendar coincided with the height of the Protestant Reformation in Europe. With formal measurements in writing, rulers and priests can extract their tithes and taxes in known quantities of commodities of grain, oil, domesticated animals, metals, etc., with consistency. Formal measurement systems and meanings meant that standardized and specialized commodities could be used in an economic way. The stamped coin attempted to formalize the value of metal by regulating content and size. Commodities are able to withstand relatively long periods of storage, which allows trade and commodity banking. In contemporary times, as well as ancient, storage and collection of taxes, etc., is carried out by specialized clerks familiar with bureaucratic accounting practices in conjunction with memory aids, such as writing and formal measurement standards. Institutions are a natural place for such formalized technologies to originate because they centralized hierarchical authority and provided a specialized community where oral agreement on meanings and rules could formulate and authority prevail. Today's government, organized religions, schools, hospitals, and other institutions carry on this endeavor to codify behavior through policy and regulation. What had been before an arrangement of convenience becomes formally standardized by institutional authority. Mechanical measurements, rationalization. The needs of machines introduced a different system. Mechanical measurements are qualitatively different from their formal predecessor. A machine which relates power to work in a linear cause-effect way needs a consistent measurement throughout so that the disparate parts may be coordinated. This difference manifests itself in decimalization and rationalization. In Greece and Rome, the light of day was divided into 12 hours, as was the dark of night. As the seasons changed, so did the length of the hours. When using a sundial and the sun was out, this was not a problem. But how to tell the hours of night without staying up and watching the stars? The first mechanical clocks were water-driven and used to regulate, amongst other things, monastery life. In the late medieval days in Europe, a mechanical alarm clock that used gravity was invented to wake sleepy monks for late-night liturgical services. The word clock comes from the Latin clocca, meaning bell. The mechanical clock keeps regulated horological time, identically long hours of day and night. Mechanically derived hours were exactly sane, whether winter or summer, rain or shine, and could be projected into the future or transposed on the past. Mechanically derived measurements of length were not formally defined until the late 18th and early 19th century by the French and English. The French developed the mechanically derived metric system. The meter was originally defined as a 10 millionth section of the arc between the equator and North Pole through Paris, as determined by mechanical surveying instruments. Two crews started from known points to the north and south of Paris and worked to the center. However, this was during the turmoil of the French Revolution. Their lives were in danger many times, both when they were thought to be royalist sympathizers or patriot revolutionaries. Their measurement in royal feet inches was surprisingly close considering the circumstances. However, for practical purposes, a formal special alloy metal standard was created to approximate this natural ideal, which was conveniently close to the French equivalent of a yard. After the French Revolution, the government legislated that time be decimalized on a macro scale. A day was divided into 10 parts, and the week consisted of 10 days, and there were 12 months of 30 days apiece with a 5 to 6 day Patriot holiday to follow. The attempt to decimalize time was met with much resistance. Perhaps people resented the longer work week, and this resulted in the decapitation of the decimal architect of time. So the metric system still divides the macro units of time sexagesimally, though seconds are divided decimally. In 1824, the English system of measurements mechanically defined the yard as a section of a pendulum swinging a second of time at Greenwich, thereby linking time and space. This interpretation did not last long, and soon both the Americans and British were defining their yard as a decimal section of the special alloy formal meter kept under special conditions at the International Bureau of Weights and Measures near Paris. Both mechanical systems tried to unify all measurements to the lineal decimal qualities of length, time, mass, and temperature, but on a popular level have had only mixed results. In countries like the Netherlands and Canada that use the metric system, recipes are often still given in teaspoons and cups or with fractional equivalents, 3/4 of a liter or 1/3 of a kilogram. But like the US and England, machine parts that have the need for exactness past the 10,000th place is based on the meter near Paris. Decimalization is characteristic of mechanical technologies striving for rationality. Decimals are easier to add, subtract, multiply, and divide using modern paper and pencil technologies and adding machines. We still use the non-decimal ways when ordering a half or a third of a piece of cheese, but use the decimal system when buying mechanically processed and packaged cheese, i.e. 1.45 ounces. Electronic measurements, ubiquitousness. While mechanical technologies try to reduce all measurements to space, time, and temperature, electronic technologies try to reduce it to just time. The electronic measurement of length becomes legally defined as the fraction of a second it takes a photon of light to travel in a vacuum. 1/299,792,458th of a second. Notice how it's not decimal. This standard may be worked out in labs equipped to use electronically broadcast time signals. Electronically determined measures are used by electrical engineers and in microchip construction. Time has been electronically reinterpreted as well. The prime unit of time is now defined as a certain number of vibrations of the cesium atom. Atomic clocks keep more regular time than either the rotation of the Earth or the Earth traveling around the Sun, hence the introduction of leap seconds in order to bring sun time and electronic atomic time more equally in line with one another. Weight and mass, however, continue to be a bafflement. A kilogram was mechanically defined as a quantity, 1,000 cubic centimeters of water, but whose water and at what temperature, etc., led to the creation of a prime physical standard, Lagrange K. At the International Bureau, there is a concern because Lagrange K is losing mass faster than the secondary measurements, national standards, which are handled much more often. The evolution of measurement technologies has reflected the change in the technological environment and reflects different relationships to reality. Contingent measures encourage a mythological worldview. The fish was this big, hold your arms out. A formal measurement system enforces institutional hierarchy and encourages a conceptual worldview. When a mechanical measurement is used, it reflects a mechanistic worldview more appropriate to machines than institutions or storytelling. It is more appropriate to use electronically derived nanomeasurements when creating computer chips than measuring a quantity of grain. To this day, the more appropriate technology is used over the metric zealots' insistence of the ease of their system for all uses.